You studied several different types of functions this year, and today you're going to look at exponential functions with respect to growth and decay. And what I'd like you to be able to do is to write and evaluate exponential expressions that model growth and decay. So in section 7.1, you're going to work with functions where the variable is in the exponent. So all of our other functions, the variable was not in the exponent. These functions are called exponential functions, and you can think of that because the variable is in the exponent. And the base is going to be b, and it is a constant, and the exponent x is the independent variable. All right, so you can look at the function, and everything is outlined for you here, or labeled. The function here, b is your base, x is the exponent. Now b needs to be greater than 0, and b cannot equal 1. The graph to the right represents the exponential function 2 to the x. Now what I want you to notice is that as the value of x decreases, the function gets closer and closer to the x-axis, but it's not going to cross it because 2 to the x cannot equal 0. So you can try that on your own and see if you can find a variable that you can put in for x to make 2 to the x equal to 0. An asymptote is a line that a graphed function approaches as the value of x gets very large or small. So the x-axis here would be our asymptote. The function is approaching it, but it's not crossing over it. Now a function of the form f of x equals ab to the x, where a is greater than 0 and b is greater than 1, is an exponential growth function, which increases as x increases. So the example that I gave you here is an exponential growth function. It starts to spike as the numbers for x get larger and larger. Now when b is in between 0 and 1, and we're not going to say less than 1 because that takes us into the negative values, and that, remember, when we have a negative, it's like the opposite, which reflects a function. So when b is in between 0 and 1, the function is called an exponential decay function, which decreases as x increases. To determine if a function represents exponential growth or decay, look at b, and that's the base that the number of the number with the exponent. Okay, now we're going to look at this function, f of x equals 10 times 3/4 raised to the x power. I'm going to have you fill in the table with these values that I'm giving you, and I just substituted those values for x into the exponent here and got all the values for y. Now when you go to graph this, you'll notice it's not a line, and it starts high and then it flattens out. So what you want to do, now I picked these points for you, but what you want to do when you pick your points is you need to choose enough points to get the flat part of the graph and the part where the graph spikes. So if you just get this much of the graph, that's not enough to represent what the graph looks like. So again, make sure that you have a flat part of the graph and also a spike. All right, now we're going to look at growth and decay. You can model growth or decay by a constant percent increase or decrease. And I'm going to show you what that function looks like. Okay, here is the function. And the rate of increase you need to write as a decimal. Quite often it'll be given to you as a percentage, but you need to write it as a decimal. So we'll just fill in these blanks here with everything. Just transfer this information over to here. A of t represents your final amount. And then you have A, which is your initial or your starting amount. Then you have your rate, which is your rate of increase. And again, that needs to be written as a decimal. And then t is the number of time periods that you're talking about. So when the base is 1 plus r, it's called growth because this is going to get larger. When it is 1 minus r, it is called decay. And we're just doing, it's kind of like the quadratic formula where you put plus or minus here so you don't have to write it out twice. Okay, let's do an example. In this section, you will use graphs and guess and check methods to solve this problem. In later sections, you're going to use logarithms to solve the problem more efficiently. So the problem is that Clara is going to invest $5,000 in an account that pays 6.25% interest per year. Now remember, we need to change this to a decimal, which means we need to move the decimal 2 places. So this is going to be 0.0625 when we put it into the function. So we want to figure out after how many years her investment will be worth $10,000. Okay, I made another table here. And this is our function. We need to figure out what values to plug in where. This is the initial amount. This is our rate. And we want to know when it's going to be worth $10,000. So here is our function. And the $10,000 would go here because later in the chapter we're going to learn how to solve this without doing guess and check. But right now I'm just going to have you do some guess and check so you can see what happens as the exponents get larger, what happens to the function. All right, I'm starting out with 1, and that's only going to give us a little over, this is 1 year, a little over $5,000. So I chose some other values. Then I jumped to 5, and still not close to $10,000. So then I went to 10, and getting closer here at 9,167. So I jumped a couple more years and went to 12, and now I'm over. So I played around with a couple of numbers, and the closest that I could get, I did 11.5, and that was 10,040, and then I went down to 11.4, and that was the closest that I could get, 9,979. I mean, I could take this out a few more decimal places, but I just took it out to the nearest tenth. So you can see what happens when you're in the lower numbers here. It doesn't grow very quickly, but as you get to the upper numbers, it does jump quite a bit more. Here there was a difference of 4. Here there was just a difference of 2. Okay, now I'm going to have you try a few questions.